Hello everyone. So today I'm going to discuss the magnitude comparator. It's one of the circuits in relation to combinational logic design or combinatorial logic. And in this specific example, we're required to design a circuit to compare between two inputs or two numbers, A and B, each of them made up of 2 bits. And the output of this circuit would be one of 3 things: a greater than or less than or an equal. So such that if A is indeed greater than B, then the greater than output would give a logic 1 or a logical high signal. Otherwise, it would give a logical low. And the same thing could be repeated for the other 2 outputs. Now, in order to start thinking about such a problem, we ideally think of the 4 steps of combinational logic design. First of all, we start sketching the problem, identifying the number of inputs. In this case, there's 4 of them, and the number of outputs. In this case, there are 3 of them, right? This leads to the next step of the design, which is tabulating the truth table. Having 4 input variables gets us to think of the number of rows of the truth table, and this is basically 2 to the power of 4, or 2 to the power of the number of input variables, giving us a truth table having 16 rows and 4 columns for the inputs as well as 3 columns for the outputs. And this would then give us this truth table as we expect to have. The next step should be the simplification of the Boolean expressions for each of the 3 outputs we have right here. So we start off with the greater than. We examine for every row of the numbers A and B. If actually A is indeed larger than B, then we have a 1 here. Since this is not the case for the first 4 rows, we have 4 zeros in this column. Only in the 5th row we start having this 0, 1 here for A and 0, 0 for B, and this is the first instance we start getting a 1 in this column. We keep on doing this, comparing the numbers A and B and writing 1s whenever this isn't true, whenever this is indeed true for the outputs, the output for the greater than. We do this again whenever the 2 numbers are indeed equal. So you can see here for the very first row, we have both numbers A and B being in fact equal, so we have a 1 here. This repeats again in this row where A is 0, 1, B is also 0, 1, so once again we have a 1 here, and then we have this a couple more times. Finally, for less than, if A is indeed detected to be less than B, then we write our numbers or our 1s in the output here. The next step would be taking these 1s and starting to writing down our K-maps. So for the first output, which is the greater than, we notice where the 1s are. We write them down in our K-map. Since we already know that we have 4 inputs, so we know that the appropriate size is a 4x4 K-map. This is exactly what we have here, or a 4 variable K-map, or a 16 cell K-map. And we start plotting our 1s and forming our groups. It's very clear that we have 4 1s here that constitute a very nice group of 1s, and then we still have a single 1 on its own here and a single 1 on its own here. As we've discussed before, it's always better to make the group of 1s as large as possible. So we take the 1 right here with the 1 on the left. They are indeed adjacent, and they form a group. I call it the pink group. And then I also form a group, I call it the purple group here between these 2 1s, and start reading out their corresponding literals, right? So, for example, in the green group right here, we have the 1s taking on values in a couple of rows. And in these 2 rows, the values of A1 and A0, here it's 1, 1, here it's 1, 0. It's clearly the case that the variable A0 is the one that changes from a value of 1 to a value of 0. So we basically cancel it. We just keep our A1 and we write it here. And then the 1s in this group are actually also available in a couple of columns. For these columns, we have B1, B0, and B1, B0 here. It's clear that B0 is the variable that changes, so we cancel it, and we maintain having the values of 0 here and here for B1. So we write this as B1 dash. We do the same for the other 2 groups, and since the other 2 groups are only made of a couple of 1s each, it's very logical to have them represented in larger min terms, as we've discussed before. As the number of literals in a min term increases, the actual number of ones in a group decreases. We do the same for the equal, and we obtain the equal output. We obtain the Boolean expression for it, and also the same for the less than. The next logical step to do here, or step number 4, is where we sketch the logic diagram. So we take our three expressions, our three simplified expressions, and we start sketching them. So this is the first one for the greater than, where a is greater than b. If this is the case, the output here would be 1. And it's a very simple implementation, as the Boolean expression suggests, using only and as well as or gates. The same can be done for the equal and for the less than. The previous example compared 2-bit numbers resulting in a truth table with 16 rows. Now, clearly, if we're interested in comparing two numbers that are larger, then the design complexity would increase rapidly. Thus, we need a way to design magnitude comparators and at the same time does not follow the usual 4 steps of combinational logic design. The following slides outline the design procedure for a magnitude comparator that takes as input two 4-bit numbers, and such an example can then be easily extended to deal with larger numbers. So consider two numbers with 4 bits each. So the number a having values a3, a2, a1, and a0, and b in the same manner designated with b3, b2, b1, and b0. These two numbers would be equal if all pairs of their significant digits are equals. In other terms, if a3 is equal to b3, a2 equal to b2, a1 equal to b1, and finally a0 equal to b0. Since these numbers are binary, the digits are either 1 or 0, and the equality of each pair of bits can be expressed logically with an XNOR function as the following expression. So xi, where I is counted, that runs from 0 all the way up to 3, is equal to ai or ai dash bi dash, such that xi is equal to 1 only in the case of both bits, or the pair of bits in position I, are equal. So they're either both equal 1 or both equal 0, and this actually follows naturally from the truth table of the XNOR function, as we've discussed in lecture 1. You only have an output here of 1 when both inputs are either equal to 0 or equal to 1. Now, we don't really care if they're equal to 0 or equal to 1, but we do care about that both digits of AI and BI are exactly the same. So for equality, it really is easy. We just need something that implements this for every value of I going from 0 all the way to 3. To determine whether A is greater than or less than B, we inspect the relative magnitudes of pairs of significant digits. We do so by starting from the most significant position, A3 and B3. And if the two digits of a pair are equal, we compare the next lower significant pair of digits. This comparison continues until a pair of unequal digits is reached. If the corresponding digit of A is 1 and that of B is 0, we conclude that A is greater than B, otherwise A is less than B. The sequential comparison can be expressed logically by the following two Boolean functions, and by examining the first one and specifically how it looks like a sum of products, this allows us to realize that if any of these min terms, if any one of them on their own, is equal to 1, then the whole expression would evaluate to 1, giving us a value or a clear signal that A is indeed greater than B. Now, if we examine the first min term here, A3, B3 dash, and we assume that A3 is 1 while B3 is 0, then actually this is going to be 1 ANDed with 0 dashed, which is 1. So 1 ANDed with 1 is going to be 1. And this indeed gives us a true or a logical high expression or value for the whole expression, signifying that A is greater than B. However, if A is 1 and B is also 1, then B3 dash here is going to be 0, and this expression will no longer give us what we're looking into, what we're expecting. So this is going to evaluate to 0, and we have to move on checking the next expression. Now, comparing the second pair of most significant bits, which is A2 and B2, this is understandable here, but we have this extra literal. It says x3. Keep in mind that x3, or all the xi's, were basically the XNORing operation of AI and BI, right? So when I read here x3, this actually means that I'm XNORing A3 and B3, right? So since we already checked that A3 and B3 are equal to each other, let's assume for the time being that they're both equal to 1, then x3 is basically a literal telling me that the previous or the prior comparison has already resulted into a 1 and didn't really give me any good information that would tell me that A is greater than B or not, right? So that's why we're now checking for A2 and B2. Now let's assume that A2 is indeed, we already talked about A3 being a 1. Let's assume that A2 is also a 1 and B2 is also a 1, right? Now this would give, or sorry, that B2 is a 0, so B2 dash would be a 1. If A2 is a 1, B2 is a 0, and thus B2 dash is a 1, this means that A2 is indeed greater than B2, and this expression would, the ending of three ones would evaluate to a logic 1, finally giving an output of a 1 for the expression right here of A greater than B. Now this same thing, the same idea of thinking about whether A or greater than B or not is continued for the other pairs of bits, assuming that A3, B3 are equal to each other, A2 and B2 are equal to each other, then we move on to A1, B1, and if we don't get any good information out of it, then we move on finally to the least significant bits, A note and B note. Now, if you're able to understand this concept of how we compare pairs of bits to check if A is greater than B, then it makes perfect sense that we just flip or complement these two values, becoming A3 dash, where we compare it to B3, and also the same for A2 dash, comparing it with B2, or expressing or checking the value of this term in such a manner, you easily understand why this expression would give a valid value for A less than B. Now, this is actually how the circuit looks like to compare two numbers. Each of them is made up of 4 bits, and while it might seem uh, as a large circuit initially, it actually is not. If we examine each of these smaller parts right here, this is actually the implementation of the XNOR, having two input variables, A3 and B3, and having the output X3. We've already written the expression for Xi, or the expression that checks for the equality of the 2 bits, right? And the same thing could be read or examined if we're interested in checking if A is greater than B, or the output would be given here. This is the O-ring of the 4 minterms in this Boolean expression. And it really is easy to see how this Boolean expression transforms into this logic diagram. And finally, the last expression for A less than B, as you can see here also, uh, it follows the same norm. Now, the nice thing about this is that it really is simple if you understand how to compare two numbers. Each of them is represented in terms of 4 bits. If you want to compare larger numbers, you can just increase the number of elements or logic gates in this circuit right here, producing another one that compares, for example, two numbers, each of them made of or consisting of 5 bits.